A dying star unleashes the universe's most powerful explosion in a blinding flash of light. These are gamma ray bursts, cosmic messengers screaming across space and time from the very edge of everything we can see. By the end of this journey, you will understand how these fleeting blips of energy hold the keys to the universe's greatest secrets, from the birth of the first stars to the very fabric of reality. We will explore what happens when matter is ripped apart by a newborn black hole, and how a blast seen from 7.5 billion light-years away was once bright enough to see with your own eyes. What single cosmic mystery would you most want a beam of ancient light to reveal that brilliant flash is a gamma-ray burst, a sudden and immense eruption of energy? These events are the most powerful explosions the universe has produced since its own violent birth in the Big Bang. For a few fleeting seconds, a single gamma-ray burst can outshine every star in every galaxy combined, releasing more energy than our Sun will emit across its entire 10 billion-year lifetime. This energy arrives in the form of gamma rays, which are the most energetic and penetrating type of light in the cosmos. These cataclysms do not happen in our cosmic backyard. They are colossal fires igniting in the distant darkness, their light traveling for billions of years before our telescopes finally catch a glimpse. Astronomers have discovered that these titanic blasts come in two distinct flavors, like two different kinds of cosmic fireworks. There are long bursts, which last for more than 2 seconds and are thought to signal the spectacular death of a massive star. Then there are short bursts, incredibly brief flashes lasting less than 2 seconds, which are believed to be the even more violent result of two ultra-dense stellar corpses, like neutron stars, crashing together. Each type is a unique signature of a universe in constant, often violent, motion. But what cosmic engine could possibly generate such an unimaginable amount of raw power, and how can we begin to understand the forces at play from so far away? That unimaginable power has a name, and one of its most distant echoes is known as JRB 090423. In April 2009, satellites detected a flash of gamma rays that lasted for barely 10 seconds. It was a seemingly ordinary short burst, but when astronomers swiftly pointed their most powerful ground-based telescopes toward its fading afterglow, they discovered something extraordinary. The light from this explosion had been traveling for 13.1 billion years to reach us. This means the star that died in this cataclysm did so when the universe itself was in its infancy, a mere 630 million years old. To put that into perspective, this burst happened so long ago that our own Sun and Earth would not even exist for another 8 billion years. JRB 090423 is not just an old signal, it is one of the most distant objects humankind has ever observed. Its light is a fossil, a time capsule from an era so ancient it is often called the Cosmic Dark Ages. This was a time before most galaxies had fully formed, when the universe was shrouded in a thick fog of primordial hydrogen gas. The fact that we can see this burst at all means its brilliant flash was powerful enough to begin burning through that fog, a process called reionization that eventually cleared the universe and made it transparent to light. So when we observe this single flash, we are not just watching a star die, we are witnessing one of the very events that helped sculpt the early cosmos into the star-filled universe we know today. What other secrets are hiding in the light of these ancient cosmic beacons? That ancient light from the burst carries a hidden code within it, a stretch mark on the fabric of spacetime itself. This code is called redshift. Imagine the sound of a siren on a passing ambulance. As it moves away from you, the sound waves stretch out, lowering the pitch. Light behaves in a very similar way. Because our universe is constantly expanding, the light from a distant object like a gamma-ray burst is stretched as it travels across the cosmos over billions of years. This stretching shifts the light from its original, energetic color toward the redder, longer wavelength end of the spectrum. The more the light is stretched, the higher its redshift value and the farther away the object is. For GRB 090423, astronomers measured a staggering redshift of 8.2. That number is not just a label, it is a direct measure of cosmic expansion. A redshift of 8.2 tells us that during the 13.1 billion year journey of that light, the universe itself has expanded by a factor of 9.2. Every single point in space is now over 9 times farther apart than it was when that burst first flashed into existence. This is how we transform a fleeting flash of light into a precise measurement of both distance and time. It allows us to place these cosmic explosions on a map of the early universe, turning them from mysterious blips into landmark events that help us chart the history of everything. So, what kind of star could create such a beacon across the ages? The leading suspect for these long-duration gamma-ray bursts is a cosmic titan meeting a violent and spectacular end. We're talking about the collapse of a massive, rapidly spinning star, a true behemoth that may have been dozens of times more massive than our own Sun. Its life is a frantic race between nuclear fusion in its core and the crushing force of its own immense gravity. For millions of years, fusion wins, but when the star finally exhausts its nuclear fuel, that race ends in an instant. Gravity wins catastrophically, and the star's core collapses in on itself. In the most extreme cases, this collapse does not form a dense neutron star. It forms a black hole. Now, here is where the star's rotation becomes the key to the entire explosion. That rapid spin acts like a cosmic whirlpool, focusing the star's dying energies into two incredibly narrow, powerful jets. These jets, moving at nearly the speed of light, drill their way out through the star's outer layers and blast out into space. The gamma-ray burst we detect is the direct result of one of these jets, by sheer cosmic chance, being pointed directly at Earth. We are essentially looking straight down the barrel of the universe's most powerful cannon. And why are these events so common in the distant, early universe? It is all about the star's chemical makeup. The first stars formed from the pristine hydrogen and helium left over from the Big Bang, lacking the heavier elements, what astronomers call metals, that later stars would possess. This low metallicity environment is crucial. It allows stars to retain more of their mass and spin much faster throughout their lives, creating the perfect conditions for this specific, jet-driven collapse. Often, this entire process is so violent that it triggers a superluminous supernova, an explosion that can outshine an entire galaxy. So a single distant flash of gamma rays tells us a profound story. It reveals the death of a rare, fast-spinning, primordial star, the violent birth of a new black hole, and a final brilliant supernova that seeded the early cosmos with the very elements that would one day form planets and life. These first-generation stars are known as population 3 stars, and they are the holy grail of modern astronomy. No telescope has ever directly seen one. They were titans in the truest sense, composed only of hydrogen and helium, the raw ingredients forged in the Big Bang. Without heavier elements to help them cool and fragment, these stars could grow to staggering sizes, potentially hundreds of times more massive than our Sun. They lived fast and died young, burning through their nuclear fuel in only a few million years before collapsing in cataclysmic explosions. The most distant gamma-ray bursts offer our very first, and perhaps only, chance to witness the death of these primordial leviathans. When a population 3 star reached the end of its life, its low metallicity core was the perfect engine for a gamma-ray burst. Its violent collapse and rapid spin would have funneled those unimaginable energies into jets of light and matter, punching through the early cosmic fog. In its death throes, this first star would have forged the universe's first heavy elements like carbon, oxygen, and iron, and then scattered them far and wide in the subsequent supernova. Every iron atom in your blood, every calcium atom in your bones, was originally forged inside a star that lived and died long before our sun was born. The very possibility that a fleeting gamma-ray burst could be the final signature of a population 3-star connects us directly to the origin of everything. It means we are using the universe's most violent explosions to illuminate its very first generations of stars, the ones that lit the cosmic dark and began the long process of building a world like our own. This energy output is almost impossible to grasp. To quantify it, picture our sun, a vast nuclear furnace that has burned steadily for 4.6 billion years. It will continue shining for another 5 billion, bathing our solar system in light and warmth across its entire 10 billion year lifespan. A single, typical gamma-ray burst in the span of a heartbeat releases more energy than our sun will across all those eons. This is not a gentle release of power, it is a cosmic detonation of almost unimaginable ferocity, but the raw energy is only half the story, the other half is focus. All of that cataclysmic force is not exploding outward in a perfect sphere. Instead, it is channeled and concentrated into 2 narrow beams known as relativistic jets. These jets are so tightly focused that they shoot out from the poles of the dying star like twin laser beams from a celestial lighthouse. The material within these jets is not just moving fast, it is traveling at a significant fraction of the speed of light, a state physicists call relativistic. This combination of immense power and extreme focus is what makes a gamma-ray burst so brilliant. It is the difference between the gentle, widespread warmth of a bonfire and the searing, concentrated intensity of a blowtorch. When one of those beams, by sheer chance, is aimed directly at our tiny planet, we witness the universe's most dazzling and violent fireworks display from a front-row seat billions of light years away. That brilliant flash of gamma rays is just the opening act. The true investigation begins with what comes next, a slowly fading cosmic fingerprint known as the afterglow. When the initial beam of gamma rays shuts off, the story is far from over. The material in those relativistic jets is still plowing outward at near light speed, slamming into the thin wisps of gas and dust that float in the interstellar void. This colossal collision acts like a cosmic brake, violently decelerating the jet and converting its immense kinetic energy into a broad-spectrum glow that can last for days or even weeks. This is the afterglow. Unlike the initial, needle-sharp beam of gamma rays, the afterglow radiates across the entire electromagnetic spectrum, from energetic X-rays all the way down to long-wavelength radio waves. For astronomers, this is the crucial turning point. The initial gamma-ray burst is so brief and localized that it is nearly impossible to pinpoint its origin. But the lingering afterglow gives them a target. They can swiftly train massive optical telescopes on that patch of sky, searching for a new, fading point of light nestled within a distant galaxy. They can aim X-ray observatories to see the high-energy remnant of the shock, or use radio dishes to listen to its low-energy echo. Each wavelength reveals a different piece of the puzzle. The optical light confirms the distance and identifies the host galaxy, the X-rays trace the most energetic processes, and the radio emissions can tell us about the surrounding environment. It is this multi-wavelength treasure hunt, made possible by the afterglow, that transforms a mysterious blip of energy into a detailed cosmic case file, allowing us to read the history of the explosion and its home galaxy long after the first light has faded. Before the afterglow fades, astronomers have a narrow window to act. This urgent need for speed gave rise to a specialized cosmic sentinel NASA Swift satellite. Named for its agility, Swift was designed with one primary mission: to catch gamma-ray bursts in the act. Its three powerful telescopes work in perfect harmony. The Burst Alert Telescope is the watchman, constantly scanning huge swaths of the sky for the sudden flash of gamma rays. The moment it detects a burst, Swift doesn't wait for commands from Earth. It autonomously and rapidly slews or spins around to point its two other telescopes, the X-ray telescope and the ultraviolet optical telescope, directly at the new target. This entire complex maneuver happens in less than a minute, a breathtaking feat of robotic precision happening automatically in the void of space. Before Swift, pinpointing a burst's exact location was a slow and uncertain process, often taking hours. Swift transformed that, delivering precise coordinates to observatories around the world within seconds. It acts as the universe's most efficient dispatcher, sending out a global alert that puts every major telescope on the planet on high alert. This automated chain reaction is what made the study of GRB 090423 possible. Without Swift's rapid response, that ancient flash would have been just another unremarkable blip in the data, its profound distance and significance lost forever. By turning fleeting bursts into long-term subjects for study, this one satellite has given us our first real-time look into the universe's most violent and ancient explosions. While Swift provides the rapid response, another telescope delivers the raw power. The Fermi Gamma Ray Space Telescope sees the universe in a way our eyes never could, observing the sky in the most energetic form of light, gamma rays itself. Fermi's specialized instruments are not designed just to locate bursts with Swift's speed, but to dissect their highest energy heart. It captures the full fury of a gamma-ray burst, measuring photons with energies millions of times greater than visible light. These are not just particles of light, they are cosmic bullets, carrying the signature of the most violent acceleration processes in nature. When Fermi observes a burst, it is probing the fundamental physics happening within those relativistic jets. The detection of these ultra-high-energy photons tells scientists that subatomic particles, like electrons, are being accelerated to velocities infinitely close to the speed of light within vast magnetic fields. It is like studying the inner workings of a cosmic particle accelerator trillions of times more powerful than anything we could ever build on Earth. Some of the most energetic photons ever recorded by humanity have come from distant gamma-ray bursts, each one a tiny messenger from the edge of a newborn black hole, revealing how matter and energy behave under the most extreme conditions the universe can conjure. This cosmic stretching presents a profound challenge for our hunters. The very expansion that gives us the redshift measurement also steals the burst's initial punch. As the light from a distant gamma-ray burst travels across an expanding universe, its wavelengths are stretched far beyond their original form. The most energetic gamma rays, born in the heart of the cataclysm, get stretched into less energetic X-rays. Some of the original X-rays may even be stretched into ordinary ultraviolet or visible light by the time they reach us. Imagine a brilliant violet laser beam fired from a galaxy billions of light years away. By the time that light finally arrives at our telescopes, the universe's relentless expansion has transformed it into a dim, deep red glow. This is the observational hurdle we face. The most distant, and therefore most ancient, bursts have their highest energy signals diluted and shifted out of the range where they are easiest to detect. They are cosmic whispers where we expect screams. This is why instruments like those on the Swift and Fermi telescopes are so vital. They are not just looking for bright flashes, they are exquisitely tuned to catch the faint, stretched remnants of the universe's earliest explosions. Their sensitive detectors must sift through the background noise of the cosmos, searching for that one, faint signal that has been traveling for over 13 billion years, a ghost of a titan's death from the dawn of time. These brilliant flashes do far more than announce their own violent birth. They act as the universe's ultimate lighthouses, casting a piercing beam that illuminates the cosmic void between galaxies. When the intense light of a gamma ray bursts afterglow journeys toward us, it does not travel through empty space. It passes through vast, invisible clouds of primordial gas, the raw material from which the first galaxies were built. As this light pierces these clouds, the gas leaves its unique fingerprint on the beam. Specific elements within the clouds, like hydrogen, helium, and the first traces of heavier metals, absorb very specific colors or wavelengths from the burst's broad spectrum of light. This process creates dark lines in the otherwise smooth rainbow of the afterglow's spectrum, like a barcode imprinted by the cosmos. Astronomers can then decode this barcode. Each absorption line tells them exactly what element the light passed through, and the degree of redshift reveals how far away that particular cloud is. A single, distant burst can illuminate multiple clouds at different distances along its path, creating a layered timeline of the universe's chemical composition. It is like turning on a spotlight in a dark forest, suddenly revealing every branch and leaf in its path. We are not just seeing the burst, we are seeing the detailed silhouette of everything that lies between it and us. This allows us to study the tenuous gas in the early universe, material that is far too dim and diffuse to observe by any other means. Through this cosmic accident of alignment, the most destructive events in the universe become our most powerful tools for cosmic archaeology, letting us take a core sample of the cosmos billions of years before our own world even existed. This cosmic fog was the defining feature of the early universe, a vast shroud of neutral hydrogen gas that filled all of space. For hundreds of millions of years, this fog rendered the cosmos opaque, trapping the light of the very first stars and galaxies. Then something dramatic happened. A great transformation began, a process astronomers call the epoch of reionization. The intense ultraviolet light from those first generations of stars and galaxies began to burn through the fog, stripping electrons from the hydrogen atoms and turning them into a transparent, ionized plasma. This was the universe's final transition from darkness to light, the moment it became the clear, observable cosmos we see today. The most distant gamma-ray bursts are our only time machines to this pivotal era. When the light from a burst like JRB 090423 began its journey, it was moving through a universe still largely cloaked in that primordial hydrogen fog. As that brilliant flash traveled, it interacted with the gas, and the specific patterns of absorption in its afterglow carry a perfect snapshot of the conditions at that exact time. By analyzing this fossilized light, astronomers can determine what percentage of the hydrogen along its path was still neutral and what fraction had already been ionized. It is like finding a sealed letter from a time when the global thaw was just beginning, telling us how much ice still covered the landscape. Each distant burst provides a single data point, a pin on the timeline of this cosmic dawn. By collecting enough of these pins from bursts at slightly different distances, we can slowly map the progress of reionization itself, understanding when it started, how quickly it progressed, and what kind of objects, whether early galaxies or voracious black holes, were primarily responsible for clearing the cosmic air. These catastrophic explosions are thereby illuminating the universe's own birth into clarity. Yet even with these cosmic lighthouses, we rarely see their light without aid. But on one extraordinary day in March 2008, the universe delivered a display that defied all expectation. A gamma-ray burst designated JRB 080319b erupted in the constellation Boötes. It was instantly remarkable, saturating detectors on the Swift satellite with its intensity. But it was what happened next that stunned astronomers and casual skywatchers alike. For about half a minute, this burst flared with such incredible brilliance that it was, theoretically, visible to the naked human eye. Anyone looking at that exact patch of sky at that exact moment, with exceptionally dark and clear conditions, could have seen a faint star wink into existence and then vanish. The sheer audacity of this event is almost beyond belief. This flash of light did not come from our galactic neighborhood. It originated from a staggering 7.5 billion light-years away. To put that distance into a human perspective, the explosion actually occurred before our own planet Earth had even formed. Its light had been traveling for more than half the current age of the universe before it reached us, and for a few fleeting seconds, it was bright enough to be seen without a telescope. This was not just a record-breaking event, it was a profound cosmic coincidence. The jet from this cataclysm was not merely pointed in our general direction. It was aimed with near-perfect precision, like a laser sight zeroed in directly on our solar system. We were looking straight down the very center of this cosmic cannon. This perfect alignment is what astronomers call an on-axis event, and it revealed a crucial detail about the structure of these relativistic jets. The jet is not a simple, uniform beam of energy. Instead, it has a complex internal structure with an incredibly bright and narrow core surrounded by a wider, dimmer sheath of energy. The initial, dazzling flash of visible light we saw was the energy from that ultra-bright core hitting us directly. The subsequent, longer-lasting afterglow that followed across other wavelengths came from the wider, slower-moving parts of the jet. GRB 080319b, therefore, taught us that these jets have an angular structure, much like a lighthouse beam with a blindingly intense center. For one brief moment, we were not just distant observers of a cataclysm, we were the intended recipients of a message written in the most intense light the universe can produce. But the universe's fireworks come in two distinct forms. While the spectacular deaths of massive stars create long gamma-ray bursts, there is another, briefer, and even more enigmatic class of event. These are the short gamma-ray bursts, flashes so quick they can be over in less than a second. Their origin is thought to be even more violent than their long-duration cousins. The leading theory points to the cataclysmic merger of two ultra-dense stellar corpses, like neutron stars, or perhaps a neutron star and a black hole. After spiraling inward for millions of years, these two objects finally collide, sending a shattering ripple through space-time and unleashing a blinding, focused jet of gamma radiation. For a brief instant, this collision forges heavy elements like gold and platinum, scattering them across the cosmos, yet finding these short bursts at immense distances has proven incredibly difficult for astronomers. While we have observed long bursts from the universe's infancy, the most distant short bursts known are relatively nearby, cosmically speaking. This is because the mergers that create them take billions of years to occur. Two stars must first be born as a binary pair, live out their lives, explode as supernova, and then have their remnant cores slowly spiral together over eons. The universe simply has not been old enough for many of these mergers to have happened in those first few billion years. The detection of a truly ancient short gamma-ray burst would therefore be a monumental discovery. It would force us to rewrite our models of stellar evolution, suggesting that some binary systems could form, live, and die with astonishing speed in the chaotic early universe. Finding such a burst would be like discovering a fully formed ancient city where we expected only scattered tribes, revealing that the cosmic clock for building complex systems ticked much faster than we ever imagined. This connection between short bursts and cosmic collisions was spectacularly confirmed in August 2017, an event that forever changed how we observe the universe. On the 17th of that month, the twin detectors of LIGO, the Laser Interferometer Gravitational Wave Observatory, sensed a subtle shiver in the fabric of spacetime. It was not the deep thrum of two black holes merging, but a different, richer signal lasting about 100 seconds. Just 2 seconds after this gravitational wave arrived, the Fermi and integral gamma ray telescopes detected a short, faint gamma ray burst from the same patch of sky. This event, designated GW170817, was the universe performing in perfect harmony. For the first time, we had witnessed a single cataclysm through two completely different messengers, gravitational waves and light. The gravitational waves told the story of two ultra-dense neutron stars, each a city-sized object more massive than our Sun, spiraling together in a final, frantic dance. The resulting gamma ray burst confirmed that this collision had indeed produced the focused jets of energy we had long theorized, but the symphony did not end there. Observatories across the planet and in space swiveled to watch, capturing a brilliant kilonova, an explosion that painted the sky with the forged elements of gold, platinum, and other heavy metals. This single event transformed astronomy, launching the era of multi-messenger astrophysics. We were no longer just seeing the universe, we were feeling its vibrations and witnessing its alchemy, all from one distant, catastrophic merger. That faint afterglow from a neutron-star merger is more than just fading light, it is a cosmic forge in action. This phenomenon is known as a kilonova, a unique type of explosion that is both incredibly brief and profoundly creative. While a supernova marks the death of a single massive star, a kilonova is the spectacular result of two neutron stars colliding. The tremendous forces and extreme densities in that collision create a nuclear reactor of unimaginable scale. For a few days, this event blazes not with the visible light of a typical supernova, but with a powerful glow in infrared and optical wavelengths, a signature of radioactive decay on a cosmic scale. The real magic happens within the hot, neutron-rich debris that is ejected during the merger. In this chaotic environment, atoms are built at a frantic pace through a process called rapid neutron capture, or the R process. Ordinary atomic nuclei are bombarded by a flood of free neutrons, allowing them to rapidly grow into the heaviest elements in the periodic table. It is within these expanding clouds of stellar wreckage that much of the universe's gold, platinum, and uranium is forged. The gravitational wave event GW170817 provided the definitive proof. Observations of its kilonova revealed the unmistakable spectroscopic fingerprints of heavy elements like gold and cesium being created in real time. This means the wedding ring on your finger or the platinum in a catalytic converter likely began its existence in a cataclysm just like this, a violent merger that occurred billions of years ago, scattering its precious metallic dust across the galaxy. These faint cosmic flashes are therefore the universe's primary factories for the heaviest elements, connecting the most violent collisions in space to the very atoms that make up our world. The sheer power of these distant explosions naturally leads to a haunting question: what if one of these cosmic cannons was not aimed at us from billions of light years away, but from within our own galactic neighborhood? Theoretically, a gamma ray burst occurring within a few thousand light years of Earth could indeed pose an existential threat to life on our planet. The danger would not come from the initial flash of gamma rays vaporizing the surface. At that distance, the beam would be wider than our entire solar system, and while it would deliver a powerful blast of radiation, the true, lingering peril would unfold in the aftermath. The real devastation would be wrought upon our planet's fragile shield, the ozone layer. That intense wave of gamma radiation would rip apart the molecules in our upper atmosphere, triggering a cascade of chemical reactions that would systematically destroy the ozone. In a matter of days, our protective layer against the sun's harsh ultraviolet rays would be catastrophically depleted. The result would be a planet bathed in deadly levels of ultraviolet radiation. This would not be a simple sunburn, it would be a sterilizing event for the surface of the world. Land-based plant life would wither and die, collapsing the foundation of the food web. Phytoplankton in the oceans, which produce a significant portion of our oxygen, would be decimated. Any complex life caught in the open would suffer severe genetic damage, leading to a mass extinction event that could rival the one that wiped out the dinosaurs. The ghost of such an event may even be written in our own planet's deep history. Some scientists have speculated that a minor mass extinction around 450 million years ago, the Ordovician Silurian extinction, could bear the fingerprints of a distant gamma-ray burst's lethal radiation. While the probability of a nearby burst is vanishingly small in any human lifetime, the cosmic scale consequences remind us that we exist in a universe capable of both breathtaking creation and utter annihilation. But how do you measure a cataclysm that happened at the edge of time itself? Astronomers have uncovered a cosmic ruler hidden within the chaos of these explosions, a principle known as the Amati relation. This is a remarkably consistent link between two fundamental properties of a gamma-ray burst, its total energy and the peak energy of its gamma-ray photons. Simply put, the more energetically a burst shines overall, the higher the energy, or the bluer and more vibrant, its light will be at its brightest moment. It is an intuitive concept, like noticing that a larger, hotter fire also burns with a brighter, whiter flame. Another similar correlation, called the Gerlander relation, refines this further by linking the burst's energy to the properties of its afterglow. These are not just abstract curiosities, they are tools of immense power. For astronomers, these relationships transform gamma-ray bursts into something they desperately need: standardizable candles. Think of a standard candle as a light bulb of a known wattage. If you know how bright the bulb truly is, and you measure how dim it appears from your vantage point, you can calculate exactly how far away it is. In the cosmic darkness, gamma-ray bursts are the brightest bulbs imaginable. By applying the Amati relation, scientists can analyze the burst spectrum to determine its intrinsic brightness. They then compare this to how bright it appears from Earth. The difference between its true brilliance and its apparent dimness gives a direct measurement of its distance. This allows us to use these fleeting explosions as cosmic mile markers, placing them with confidence on the map of the expanding universe and tracing the rate of that expansion back through billions of years of cosmic history. That cosmic ruler, the Amati relation, gives us mile markers deep into the past, but what story do those markers tell when we connect them? The plot they reveal is one of the greatest mysteries in all of science, the accelerating expansion of the universe driven by dark energy. For decades, our best maps of cosmic expansion came from a specific kind of stellar explosion, type Ia supernova. These supernovae are brilliant and reliable, but they have a limitation. They are the fireworks of evolved stellar systems, and looking back to the universe's first few billion years, they become increasingly rare and faint. This is where gamma-ray bursts enter the stage as the ultimate deep space scouts. GRBs are thousands of times brighter than supernova, which means we can detect them at much greater distances and thus from much earlier times. By applying relations like the Amati relation to these distant bursts, astronomers can place them on the cosmic timeline with remarkable precision. Each burst becomes a single data point, a measurement of how fast the universe was expanding at the specific moment its light was emitted. When you collect enough of these points, from the relatively recent supernova to the ancient gamma-ray bursts, you can trace the entire history of the universe's expansion. And the story that history tells is bizarre. It appears that after the initial Big Bang, the expansion of the universe was slowing down, as you would expect from the mutual gravitational pull of all matter. But then, around 5 billion years ago, something strange happened. The expansion, against all expectations, began to speed up. This acceleration is attributed to a mysterious repulsive force, dark energy, which makes up about 70% of the cosmos, yet remains completely invisible. Gamma-ray bursts are our only hope of peering into the era before this acceleration began. They allow us to measure the expansion rate in the universe's youth, providing the critical early data points needed to understand the nature of dark energy itself. Was its strength constant over time, or has it changed? The answer, hidden in the light of these ancient explosions, will determine the ultimate fate of everything. Just when astronomers thought they had gamma-ray bursts neatly categorized, the cosmos revealed a new puzzle. Beyond the fleeting short bursts and the minutes-long standard bursts, there exists a mysterious third class. These are the ultra-long gamma-ray bursts, events that can shine for tens of thousands of seconds, sometimes lasting for hours on end. A typical long burst might blaze for 20 seconds or 2 minutes, but an ultra-long event defies all expectations, glowing with the power of a billion suns for what feels like an eternity in the world of high-energy astrophysics. This is not a simple extension of time, it is a fundamental difference in the cosmic engine itself. The leading theory for these marathon explosions points to the death of a truly unique kind of star, a blue supergiant. Unlike the massive but compact Wolf-Rayet stars thought to produce regular long bursts, a blue supergiant is a behemoth with a vast, extended hydrogen envelope. When such a star collapses, that immense outer shell acts like a prolonged fuel source for the central engine. The newborn black hole has to devour this colossal amount of material over a much longer period, powering the jets for hours instead of seconds. It is the difference between a brief, intense flash of gunpowder and a massive log that burns slowly and brightly on a cosmic fire. Another tantalizing possibility is that some of these ultra-long bursts are not from stellar collapses at all, but from a different kind of cosmic disaster, a tidal disruption event. This occurs when a star wanders too close to a supermassive black hole at the center of a galaxy. The black hole's immense gravity violently shreds the star, stretching it into a long, thin stream of gas. As this material spirals down into the black hole, it heats to incredible temperatures, potentially launching jets that we see as an ultra-long gamma-ray burst. The existence of this class forces us to rethink our models of stellar death. It suggests that the final moments of the largest stars are more diverse and complex than we ever imagined, with the structure of the star itself dictating the duration and power of its final, spectacular farewell. Even the most brilliant cosmic lighthouse can be shrouded by a dense fog. This is the enigma of dark gamma-ray bursts. These are bursts where the initial flash of gamma rays is detected perfectly, but when astronomers race to look with optical telescopes, they find nothing or only a whisper of visible light where a bright afterglow should be. It is as if the universe has thrown a cloak over the explosion, hiding its final act from view. The most likely culprit is cosmic dust, and lots of it. In the vibrant, chaotic neighborhoods where massive stars are born, vast clouds of tiny, sooty dust grains fill the space. When the visible light from a gamma ray burst's afterglow tries to shine through this cosmic smog, the dust doesn't let it pass. The dust grains absorb the visible light, much like a thick blanket of fog absorbs the beam from a car's headlights. All that brilliant energy is then re-radiated by the dust as invisible, long-wavelength infrared light, effectively making the burst disappear from our optical view. This simple explanation has profound implications for our map of the early universe. If many bursts are going dark, it means we are systematically missing a huge population of these cosmic explosions. And since gamma-ray bursts trace the death of massive stars, missing dark bursts means we are missing entire chapters in the story of star formation. The most dust-rich environments are often the most fertile stellar nurseries, places where stars are being forged at a frantic pace. By failing to see the bursts from these regions, we could be underestimating just how violent and productive the early universe truly was. The mystery of the dark bursts, therefore, is not just about a missing afterglow, it is a challenge to our entire census of cosmic births and deaths, forcing us to ask what other brilliant fires are burning just out of sight. This new era of discovery now has its ultimate instrument, the James Webb Space Telescope. While Swift and Fermi act as rapid response sentinels, Webb is the deep time archaeologist designed to stare into the cosmic dawn itself. Its most profound power lies in its vision, its ability to see the universe in infrared light. Remember how the expansion of the universe stretches the light from the most distant objects, shifting it from visible blue into the deep red and infrared part of the spectrum. For a burst like GRB 090423, whose visible light has been stretched into the infrared, the Hubble Space Telescope could only see a faint smudge. But for Webb, that same stretched light is perfectly within its view. It is built to see the cosmic landscape in the exact colors it now appears. With its colossal gold-coated mirror, Webb can collect this ancient, faded light with a sensitivity that is utterly unprecedented. It will not just detect the faint afterglow of a burst from the first billion years, it will dissect its light with a spectrograph, reading its chemical composition like a detailed history book. This will allow scientists to finally answer the burning question of whether the most distant bursts truly do come from those mythical population 3 stars, the very first generation. The spectroscopic fingerprint of a star with no heavy elements would be unmistakable, a direct confirmation of a universe before metals even existed. Furthermore, Webb will turn its gaze to the burst's host galaxy, where current telescopes see only a faint blur. Webb will resolve the structure of these infant galaxies, revealing whether these early cataclysms happened in small, chaotic proto-galaxies or within more structured environments. By connecting the specific nature of the explosion to the detailed properties of its galactic home, Webb will trace the intimate link between the death of the first stars and the growth of the first galaxies. It will use gamma-ray bursts as brilliant flashlights to illuminate the nurseries where cosmic structure was first assembled, revealing a chapter of the universe's story that has, until now, been written in invisible ink. The story of these cosmic explosions begins not with a grand astronomical quest, but with the tense politics of the Cold War. In the late 1960s, the United States launched a series of top-secret satellites known as Vela. Their mission was not to explore the cosmos, but to watch for violations of the Nuclear Test Ban Treaty. These robotic sentinels were designed to detect the telltale flash of gamma radiation from an atomic detonation in the Earth's atmosphere or in the void of space. For years, they dutifully watched, and then they began to see something impossible. The sensors were being triggered by brief, intense bursts of gamma rays, but the data pointed to a source far beyond our planet. These flashes were not coming from any nation on Earth. They were originating from deep space, from random directions across the sky. This was a profound and unsettling mystery for the military analysts. They had stumbled upon a natural phenomenon of unimaginable power, one that completely dwarfed any human-made weapon. For years, the data remained classified, a cosmic secret hidden within a military program. It was not until 1973, after careful analysis to rule out any terrestrial or solar origin, that the discovery was finally declassified and shared with the scientific community. The universe had been sending us its most powerful signals for years, and we only heard them because we were listening for something else entirely. This accidental revelation opened an entirely new window on the cosmos, proving that the most dramatic discoveries often come when we are looking for something completely different. This cosmic drama unfolded in March 2011 when the Swift satellite detected a sudden flare in the constellation Draco. Astronomers cataloged it as GRB 110328A, a name that suggested a typical long gamma-ray burst. But this signal refused to fade. Instead of dimming over days, it flared again and again, shining erratically for weeks and then months on end. It was a cosmic beacon that simply would not turn off, behaving like no gamma-ray burst ever seen. The mystery only deepened when precise observations pinned its location not to a star-forming region in a distant galaxy, but to the very heart of a galaxy itself. The true identity of this bizarre object became clear. This was not the death of a star giving birth to a black hole. It was the opposite, a supermassive black hole, a monster weighing millions of times the mass of our Sun, awakening to devour a star that had wandered too close. The event was reclassified as Swift J1644+57, a tidal disruption event of unprecedented ferocity. As the star was caught in the black hole's immense gravity, it was not swallowed whole. It was shredded, stretched into a thin, spaghetti-like strand of gas in a process called spaghettification. This stream of stellar material then swirled into a vast, hot accretion disk around the black hole, like water circling a drain. The tremendous friction and magnetic fields within this disk then launched a powerful, wobbling jet of matter and radiation directly outward, and by a staggering 1 in a million chance, that jet was aimed right at Earth. We were not witnessing a star's death cry, but the real-time feast of a cosmic giant, a meal that powered a brilliant, flickering lighthouse for the better part of a year. This event blurred the line between different classes of cosmic explosions, proving that the central engines of active galaxies can ignite with stunning speed, and that a black hole's launch can mimic the universe's most powerful blasts. While the collapse of a massive star often creates a standard neutron star, nature sometimes forges something far more extreme. A magnetar is a neutron star born spinning furiously and endowed with the most powerful magnetic field in the known universe. This is not just a strong magnet, its field can be 1,000 trillion times more powerful than Earth's. To grasp that scale, if a magnetar were located halfway between the Earth and the Moon, its magnetic pull would be strong enough to strip the data from every credit card on the planet. This unimaginable magnetic energy, bottled up within a city-sized object, provides the power for a strange and less energetic class of gamma-ray flashes. These are not the single, catastrophic blasts of a collapsing star, but repeating, shorter bursts of softer gamma radiation. The leading theory suggests that the intense magnetic stress can actually crack the magnetar's solid, iron-rich crust. These starquakes release colossal amounts of stored energy, shaking the magnetar and twisting its magnetic field lines. When these field lines snap and reconnect, much like a rubber band pulled too tight, they unleash a firestorm of radiation. This process can happen again and again, making magnetars the only known sources of repeating gamma-ray flashes. They are the universe's restless powerhouses, capable of brilliant, localized tantrums that, while less energetic than a full gamma-ray burst, still outshine entire galaxies for a fleeting moment. So the next time you hear of a strange, repeating flash in the deep sky, it might not be a star's final death cry, but the violent shiver of a cosmic magnet, reminding us of the incredible forces slumbering within the densest objects in existence. These violent stellar deaths are more than just cosmic spectacles. They are fundamental physics laboratories operating at energies we can never hope to achieve on our own planet. Within the relativistic jets of a gamma-ray burst, matter and energy are pushed to such extremes that they begin to challenge our most basic understanding of reality. The photons screaming across the cosmos from these events carry with them subtle clues about the very nature of space and time. One of the greatest quests in physics is the search for a theory of quantum gravity, a single framework that unifies the large-scale rules of general relativity with the bizarre, probabilistic world of quantum mechanics. We suspect that on the tiniest possible scale, the smooth fabric of spacetime predicted by Einstein might actually be foamy and granular, a seething quantum foam. This hypothetical structure is far too small to detect in any earthly experiment, but what if we could use the universe itself as our particle accelerator? The highest energy gamma-ray photons from a burst travel for billions of years across this potentially bumpy spacetime. If space has a granular structure, these photons, each with a slightly different energy, might be jostled in different ways, causing them to arrive at our telescopes at slightly different times. By meticulously timing the arrival of these photons across a vast range of energies from a single, distant burst, physicists are hunting for this delay. Finding it would be the first experimental evidence for quantum gravity, a discovery that would reshape our comprehension of the cosmos at its most fundamental level. This search also probes the principle of Lorentz invariance, a cornerstone of Einstein's special relativity, which states that the laws of physics are the same for all observers, regardless of their constant velocity. Some theories suggest that in the extreme environment of a gamma-ray burst jet, this sacred principle might be very slightly violated. The incredible densities and energies could cause light itself to behave in unexpected ways, perhaps with its speed varying minutely depending on its energy. A high-energy gamma-ray photon might not travel at exactly the same speed as a lower-energy one. While these effects are unimaginably tiny, over a journey of billions of light years, those tiny differences could add up to a measurable signal. By analyzing the light from the most distant bursts, we are effectively conducting a precision test of relativity on a cosmic scale, using the universe's most powerful explosions to question the very laws that govern it. Every flash from the edge of time is therefore a message in a bottle, carrying within it answers to questions we are only just learning how to ask. That faint barcode of absorption lines in a burst's afterglow has its own intricate structure, a dense thicket of dark marks known to astronomers as the Lyman alpha forest. Each line is a ghost, the spectral imprint of a single cloud of neutral hydrogen gas that the brilliant light of the gamma-ray burst passed through on its multi-billion-year journey to Earth. The name comes from a specific electron transition in hydrogen atoms, which absorbs a very particular shade of ultraviolet light. Because the universe is expanding, the light from each cloud is stretched by a different amount, shifting its unique absorption line to a slightly different position in the spectrum. A cloud that is closer to us will have its line shifted a little bit toward the red. A cloud that is much farther away, and thus seen much earlier in cosmic time, will have its line shifted dramatically further. The result is not one or two lines, but hundreds or even thousands of them spread out across the spectrum like the rings of a tree, each ring marking a different year of growth. Here, each line marks a different epoch in the universe's expansion. When astronomers point their spectrographs at the afterglow of a distant gamma-ray burst, they are not just looking at the burst itself. They are collecting a core sample of the cosmos. The dense collection of lines becomes a fossil record of the large-scale structure of the universe throughout time. The patterns in this forest tell a profound story. Where the lines are clustered closely together, it reveals vast cosmic walls, immense filaments of hydrogen gas stretching across millions of light years, the scaffolding upon which galaxies would eventually form. Where there are gaps and clearings in the forest, it maps out the corresponding cosmic voids, the empty, desolate regions between those walls, a single spectrum from one incredibly distant flash of light can therefore chart the distribution of matter across a vast swath of cosmic history, from the relatively recent past all the way back to when the universe was only a fraction of its current age. This turns a catastrophic explosion into the most powerful survey tool we possess, allowing us to trace the invisible architecture of the cosmos itself. The race to capture a dying cosmic beacon begins with a single automated email. Within seconds of a satellite alert, a global network of observatories receives the call to action. This is not a leisurely scientific endeavor, it is a high-stakes treasure hunt against the clock. Professional astronomers, university students, and robotic telescopes perched on remote mountaintops all join the chase, their singular goal to pinpoint the fading afterglow before it vanishes back into the blackness of space. This coordinated global scramble is the only way to transform a fleeting satellite detection into a rich, multi-wavelength portrait of the event. Each type of telescope sees a different part of the story. Large optical telescopes on the ground, like the Very Large Telescope in Chile or the Keck Observatory in Hawaii, attempt to capture the visible light, measuring its redshift to determine the burst's immense distance. Simultaneously, space-based X-ray observatories like Swift's own X-ray telescope monitor the high-energy emissions, tracing the violent interactions within the jet itself. Meanwhile, radio telescope arrays across different continents tune in to the long wavelength whispers of the explosion, revealing details about the surrounding interstellar material. This frantic collaboration is a symphony of technology and human curiosity, with every data point captured adding another brushstroke to the picture. The afterglow is fading with every passing minute, and this global clockwork of observation is our only chance to read the message it carries from the edge of time. The hunt for the universe's first starlight is about to receive its most powerful tools yet. A new generation of space observatories is being prepared, designed specifically to push our vision deeper into the cosmic dawn than ever before. Leading this charge is the ESVAM mission, a collaborative project between space agencies in China and France. Its name, the Space-Based Multi-Band Astronomical Variable Objects Monitor, describes its precise purpose to be a relentless sentinel for the most violent and variable events in the sky. ESVAM will carry advanced gamma-ray, X-ray, and optical telescopes, but its true genius lies in its strategy. It is engineered not just to detect a burst, but to instantly calculate its distance. If a burst is deemed distant and interesting enough, ESVAM can send an alert to a network of ground-based telescopes in under a minute, all while temporarily blocking bright sunlight from the Earth to protect its sensitive optical eyes. This swift, intelligent coordination will allow us to capture the fleeting afterglows of bursts from the very edge of observable time. Following closely behind is the ambitious Theseus mission concept proposed to the European Space Agency. Theseus, which stands for the Transient High Energy Sky and Early Universe Surveyor, has an even more profound goal. It is designed to perform a complete census of the high energy sky, systematically discovering gamma-ray bursts from the first billion years of the universe. Its instruments are so sensitive they could find bursts from the era of the very first stars, the mythical population, 3 stars we have long sought. These missions represent a fundamental shift from simply catching random bursts to conducting a targeted archaeological dig into the early cosmos. They will not wait for the universe to send us a signal. They will actively sift through the darkness, collecting these ancient flashes by the thousands. With each new burst they find, we add another day to point to our map of cosmic evolution, another clue to the nature of dark energy, and another glimpse of the primordial fires that ended the universe's dark age and lit the path to our own existence. A truly dark cosmic field would be the ultimate discovery, a flash of ancient light with no galaxy to call home, a gamma ray burst detected at a staggering redshift, its light parsed and measured, would point to a specific, tiny patch of sky. Yet when the most powerful telescopes like the James Webb stare deeply at that location, they would find nothing, no swirling spiral of stars, no faint smudge of a primordial galaxy, just the profound and empty blackness of the early universe. This missing host galaxy would not be an observational error, it would be a profound clue. It could mean that the dying star was one of the true pioneers, a member of the first generation of stars to ever ignite. These population 3 stars are thought to have formed in small, dark matter halos, isolated and faint, their light far too weak for our telescopes to see directly. The catastrophic death of one, however, would be visible for billions of years. A no-host gamma-ray burst would be the ghost of a lone titan, a star that lived and died before its dark matter halo could attract enough gas to grow into a recognizable galaxy. It would be a direct signal from the era of first light, when stars flickered on one by one in an endless sea of darkness. Alternatively, it could reveal a population of stars that formed in the vast, empty spaces between the emerging cosmic web, far from the dense knots where large galaxies would later assemble. These would be the universe's true orphans, stars born from wispy, isolated clouds of primordial gas that never became part of a larger structure. Their brilliant, explosive deaths would be the only sign they ever existed. Either scenario forces a dramatic rewrite of our cosmic history. It would tell us that the first stars could die in isolation, that the universe's initial fireworks display was not confined to grand galactic stages, but also occurred in the lonely voids, seeding the cosmos with the first heavy elements long before most galaxies had even begun to take shape. Finding a burst without a home would confirm that we are finally seeing past the dawn of organized galaxies and into the true cosmic dark ages, a time when the first sparks of starlight were only just beginning to pierce the infinite night. These flashes from the edge of time are far more than cosmic fireworks. They are our guides, illuminating the entire history of the cosmos from its first stars to its ultimate fate. We have journeyed from the death cries of primordial titans to the violent mergers that forge gold, from the clearing of the cosmic fog to the mysterious push of dark energy. Each fact reveals how these distant cataclysms are not just events we observe, but active participants in the story of the universe, shaping its structure and seeding it with the elements for life. The next time you gaze up at a dark, starry sky, remember that the emptiness between the stars is not truly empty. It is a canvas alive with the invisible echoes of these titanic explosions, each one a beacon from the deep past. We would love to hear which of these cosmic truths resonated most with you. Was it the burst once visible to the naked eye from 7.5 billion light-years away, or the idea that your own jewelry contains atoms forged in a neutron star collision? Share the fact that filled you with the most wonder in the comments below. Even after decades of discovery, the central engine of a gamma-ray burst remains one of the universe's best-kept secrets. We know these cataclysms are born from collapsing stars and colliding neutron stars, but the precise mechanics within the relativistic jet are still a blur. How exactly does a newborn black hole or a hypermagnetized neutron star channel so much raw power into such a perfectly focused beam, and what chaotic processes generate those initial pulses of light? Every new burst we observe offers clues, yet the fundamental blueprint for this cosmic power plant is still missing. This leads directly to another haunting uncertainty. Are we seeing the full spectrum of these explosions, or is our current classification system merely a sketch of the true diversity? We have long bursts, short bursts, and ultra-long bursts, but what other varieties are lurking in the darkness? their light stretched into undetectable wavelengths or hidden behind impenetrable cosmic dust. Our telescopes might be tuned to only the most obvious signals, missing an entire zoo of fainter, stranger, or uniquely structured events that could rewrite our understanding of stellar death. Perhaps the most profound question stretches our view to the absolute edge. Could there be bursts from the first 200 million years of the universe, flashes from the era before even the most distant jarbi we have found? Such primordial events would be so redshifted that their light would have faded into near nothingness or been absorbed completely by the thick neutral hydrogen of the early cosmic fog. Detecting them would be like hearing a whisper from the moment the very first stars switched on. The hunt for these ultimate ghosts continues, driving the design of ever more sensitive observatories. The story of gamma-ray bursts is far from complete. It is a living field where every new flash of light has the potential to shatter old theories and unveil entirely new chapters in the cosmic saga. Keep looking up and stay curious, for the next great revelation is written in a light that has not yet